50. 50 is the same thing as 25 times 2, right? And 25 is a perfect square. So if I take the square root of 25, that's 5. And then this 2 gets left behind. Okay. Another way we could look at that is if I take 50 and I factor it completely. Any matching pairs you pull out, and then anything that's left over stays inside. Okay. If I have two radicals, the square root of 2 times the square root of 8, you multiply what's underneath together. So that's the square root of 16, which is 4. Okay. If I have radicals that match, so both of these are square root of 3, and I treat that just the same way I would, like if this was 7x plus 2x. You just add the two numbers in front and leave the radical the same. Same with subtracting. I just subtract these two numbers and leave the radical the same. And again, if I square a square root, if you multiply identical square roots times each other, the square roots go away. Theorem. In any right triangle, the area of the squares whose side is the hypotenuse is equal to the sum of the areas of the squares whose sides are the two legs. Nobody remembers all of that. Everybody remembers this. Okay? And when you have a right triangle, one of the legs is A, one of the legs is B, the hypotenuse is C, and the way you can tell which one has to be the hypotenuse is the corner of the square from the right angle points to the hypotenuse. This one has to be C. These two, it doesn't matter. This could be A, this could be A, that could be B. It doesn't, the legs don't matter. They're just one of them is A, one of them is B. But this has to be C. A Pythagorean triple is any whole number that satisfies the theorem. So a very common Pythagorean triple is 3, 4, 5. So we have three whole numbers that satisfy the theorem, and I can show you that it does, because I can say 3 squared plus 4 squared is equal to 5 squared. 9 plus 16 is equal to 25. This is true. This is a Pythagorean triple. Now once you find a Pythagorean triple, all multiples of this are also triples. So 6, 8, 5 is a Pythagorean triple, or sorry, not 5, 10. I multiplied everything by 2, right? If I multiply everything by 3, that's a triple. If I multiply everything by 4, that's a triple, etc. So any Pythagorean triple that you find, all of the multiples are also Pythagorean triples. The way they discovered the Pythagorean theorem is this: if you take a right triangle and you actually draw squares off of it, so if this length is 3, you draw a square, so it's a 3 by 3. This length is 4, so you draw 4 by 4. This length is 5, so you draw 5 by 5. If you count up all these squares, they equal all those squares. So the Pythagorean theorem, you know, the lengths of the sides squared, it's actually literally the squares off of the side are equal to, like the sum of these two squares is equal to that square. That's how they discovered it. Someone was doodling, I think, and that's how they came up with it. Okay. We can use the theorem to find missing lengths, okay? I have 5 and 12 and C. Doesn't matter which one I say is A and B. So I have 5 squared plus 12 squared is equal to C squared. 25 plus 144 is equal to c squared. So 169 is equal to c squared. And then I take the square root of each side, and c is 13. Now normally when you take the when you take a square root, you get plus or minus, right? Because it's positive 13 or negative 13. But when we're talking length, positive.
Also, all the sides are the same.
Right, so we have a square, so if this is x, this is also x.
Oh, okay.
Right?
Mm-hmm.
So I have x squared plus x squared is equal to 8 squared. Right? Because these are the legs, that's the hypotenuse. So that's 2x squared is equal to 8 squared, which is, sorry, 64. Divide by 2. So x squared is 32. I'm going to take the square root of both sides. Now 32 is not a perfect square, so I'm going to factor it. It's 2 times 16, and 16 is a perfect square. But if I didn't see that, I could keep going. Okay. Every pair of 2's allows me to bring a 2 out. So I can bring out a 2 from that pair and a 2 from this pair. And then this guy, poor lonely 2 over here, gets left behind. So everything you pull out, you multiply together.
So it would have been the same if we would have just stopped at 16.
Yeah, if you didn't know the square root of 16 though, you could do it by complete factorization. So you can either stop with the 16 and say, oh, the square root of 16 is 4, and pull that out. Or if you don't think of that, you can factor it completely and say, okay, I have one set of 2's, so I can pull this 2. So this 2 comes from here, this 2 comes from there, and this 2 is the leftover guy. And then anything that you pull out, you multiply together, and anything that gets left behind, if there's more than one, those get multiplied together. So A, B, C. So I have 24 squared plus 10 squared is equal to c squared. So 576 plus 100 is equal to c squared. So 676 is equal to c squared. And then if I take the square root of both sides, c is 26. So we took the square root of both sides. So 10, 24, 26 is another Pythagorean triple. Anytime you get a whole number, you found a Pythagorean triple. Okay. I have 6 and 10. Now I have Pythagorean triple 3, 4, 5 memorized, and these are multiples of 3 and 5. So I know what this one is, just off the top of my head. No. It's a 3, 4, 5, right? Normally that we have a 3, 4, 5. Would I multiply this and this by to turn a 3? Yeah, I multiply by 2. So this would be 8. We have Pythagorean triples, and 3, 4, 5 is the most common. So all multiples of 3, 4, 5. So if you multiply by 2, you get 6, 8, 10. So 6, 8, 10. But if you don't know it, this is A, this is B, this is C, and so you do 6 squared plus x squared equals 100 squared. 36 plus x squared equals, no, sorry, not 100 squared, 10 squared, so then 100. So x squared equals 64, so x is 8. Okay, here I have C, and I can say this is A and this is B, or vice versa, it doesn't matter. So also, I have 9 squared plus b squared is equal to 14 squared. So 81 plus b squared is equal to, darn it, I forgot my 14 squareds. 196. Subtract 81 from each side. So I get b squared is equal to 115. Okay, that's not a perfect square. I know it'll divide by 5, and that gives me 23. 23 doesn't divide by anything, so b is just the square root of 115. Okay, and then if I have a square, both of these sides are x. So I have 2x squared is equal to 24 squared. So 2x squared is equal to 576. Divide both sides by 2. And you get x squared is equal to 288. Again, that's not a perfect square, so I'm going to start dividing by 2. Actually, I'm going to do this over here on the other side. I'm not going to have enough room. So I do 288, which is 2 times 144, which is 12 times 12. Now, if I just don't stop there, I can keep going. And I have a pair of 2's, and a pair of 2's, and a pair of 3's, and a 2 left over. So if I didn't see the 12 times 12, I would have ended up with 2 times 2 times 3 times the square root of 2. If we have a fraction in there, we can still use it. Okay. So we have, a squared plus b squared is c squared, right? So this is 2 squared plus 3/4 squared is equal to c squared. When you square a fraction, you square the top, you square the bottom. Okay. Now to add these together, I need to turn this 4 into 16ths. So what I'm going to do is I'm going to multiply 4 times 16. Okay, and that's going to give me 64. So this 4 becomes 64 16ths plus 9 16ths is equal to c squared. Okay, so I'm going to add 64 plus 9, and I'm going to get 73. Okay. And then I'm going to take the square root of both sides. Now the square root of 73 16ths is the same thing as the square root of 73 over the square root of 16. You can break it in half, and I can take the square root of 16. I can't take the square root of 73, so I just leave it.